When I picture Mars, my mind goes to the planet we know today. A silent, frozen desert. A world of rust-red rock and dust, where the only water is locked away as ice. But this wasn't always the case. Billions of years ago, Mars was a world teeming with liquid water. And that's not science fiction. It's a scientific reality. The evidence is etched into the very surface of the planet. We're not just talking about a few puddles. We're talking about vast oceans that may have covered a third of the planet's northern hemisphere. And the rivers that fed these oceans, they were massive, colossal. Some were so wide they could swallow entire countries whole. This is the story of a lost world that challenges our perception of Mars. This is the story of the great rivers and oceans of ancient Mars. Our first clues to this watery past came from orbiters circling high above. Beginning with the Mariner 9 mission in 1971, spacecraft began to map the Martian surface in unprecedented detail, revealing a landscape crisscrossed with familiar-looking features. They found extensive valley networks branching across the ancient southern highlands. These systems resemble terrestrial river basins, carved by rainfall and surface runoff over immense timescales. Instruments like the Mars Orbiter Laser Altimeter created detailed topographic maps, allowing scientists to trace the flow of these ancient waterways from their highland sources down towards the vast northern lowlands. But the orbiters revealed something else, something far more violent: gigantic outflow channels. These are not the delicate branching networks of the highlands. These are gargantuan scars, hundreds of kilometers wide and thousands of kilometers long, scoured out of the Martian crust. Features like Khase Valles and Ares Vallis are evidence of catastrophic megafloods, likely triggered by the sudden release of vast underground reservoirs, unleashing torrents of water that dwarfed any flood known in Earth's history. For years, scientists debated whether these channels were carved by water or flowing lava. But the detailed morphology tells an undeniable story. We see streamlined islands shaped like teardrops where water flowed around obstacles. We see terraced banks marking different flood levels and clear evidence of erosion and sediment deposition, the classic fingerprints of water. As our rovers began to explore these features up close, the evidence became even more compelling. The Perseverance rover is exploring Jezero crater, the site of a perfectly preserved river delta. Here we can see the fan-shaped deposits of sand and mud that formed as a river slowed and emptied into a crater lake that existed for thousands, perhaps millions of years. We find sinuous meandering ridges that are the fossilized remains of ancient riverbeds, so similar to rivers like the Mississippi that they are unmistakable. The geometry of these meanders allows scientists to estimate the depth and flow rate of the water that created them. The conclusion is consistent. These were not fleeting trickles, but persistent, powerful rivers. Beyond the shape of the land, the very rocks of Mars tell the story of its wet past. Orbiters and rovers analyze the mineral composition of the surface, and what they've found is a chemical confirmation of what the geology suggests. In countless locations, we find finely layered sedimentary rocks. These layers are formed when particles of sand, silt and clay settle out of a water column. The sheer thickness of some of these deposits, like those in Gale crater, points to standing bodies of water that were stable for millions of years. Crucially, instruments have detected minerals that can only form in the presence of liquid water. We find abundant deposits of clay minerals, or phyllosilicates. On Earth, clays form when rock is chemically weathered by water over long periods. Finding them on Mars is a profound discovery, as this type of environment is considered highly conducive to the origin of life. In other, typically younger regions, we find a different class of water-related minerals, hydrated sulfates. These minerals, like gypsum, form when water evaporates, leaving behind dissolved salts. They point to a later, more acidic and salty Martian environment as the planet's climate began to change. The transition from a clay-rich world to a sulfate-rich world tells a planetary story of climate change, a story of a planet drying out. For rivers to flow, Mars needed a very different climate. Liquid water isn't stable on the surface now. The atmospheric pressure is so low it would instantly boil away. The existence of these ancient water features is therefore undeniable proof that early Mars had a much thicker, warmer atmosphere. This atmosphere would have generated the necessary pressure to keep water liquid and a strong greenhouse effect to keep the surface temperature above freezing. Climate models suggest an atmosphere rich in carbon dioxide and water vapor could have created these conditions. This thicker atmosphere would have supported a full hydrological cycle, much like Earth's. Water would evaporate from oceans, form clouds, and fall as rain or snow, feeding the very river networks we see etched into the landscape today. Ancient Mars was a dynamic, weather-filled world. So, where did it all go? Why did this warm, wet world transform into the frozen desert we see today? The answer lies deep within the planet's core. Early in its history, Mars had a molten iron core that generated a powerful global magnetic field. This field acted as an invisible shield, protecting the planet's atmosphere from the solar wind, a constant stream of charged particles from the Sun. But Mars is smaller than Earth, so it cooled faster. As its core solidified, the dynamo that generated the magnetic field shut down. Sometime around 4 billion years ago, Mars lost its shield. Without this protection, the solar wind was free to slam directly into the upper atmosphere. NASA's MAVEN orbiter has observed atmospheric gases being stripped away into space right now, confirming this process was the primary culprit for Mars's climate catastrophe. Over hundreds of millions of years, the solar wind relentlessly eroded the Martian atmosphere. As the pressure dropped, the greenhouse effect weakened. The planet grew colder, and the liquid water on its surface either froze, retreated underground, or was lost to space. The rivers stopped flowing, and the oceans vanished. The story of Martian water unfolded over billions of years. The primary period of surface water, the Noachian period, from about 4.1 to 3.7 billion years ago, was the era of valley networks and a likely northern ocean. This was Mars at its most Earth-like. Following this was the Hesperian period, marked by massive volcanic activity and catastrophic outflow floods. Finally, we entered the current Amazonian period, a long, dry and frozen age. By studying hydrogen isotopes, scientists estimate Mars has lost at least 87% of its water to space. Most of it is now gone forever. This ancient watery Mars presents a tantalizing possibility. For hundreds of millions of years, Mars had all the necessary ingredients for life as we know it: liquid water, essential chemical elements, and an energy source. This opens up a habitability window, a period when life could have emerged. The very places we see evidence of long-lived water, like the clays in Gale Crater or the delta in Jezero Crater, are prime targets in the search for biosignatures, the chemical or fossilized traces of past life. This is the core mission of rovers like Perseverance. They are astrobiologists searching for signs of ancient life in rocks, that formed in these once habitable environments. The samples being collected by Perseverance are part of an ambitious Mars sample return mission, which would bring these pristine pieces of Mars back to Earth. It would be our first chance to definitively answer the question, are we alone? The discovery of Mars's watery past has fundamentally transformed our understanding of the red planet. It is no longer just a static, icy rock. It is a planet with a dramatic history, a world that was once much more like our own before undergoing profound climate change. The country-sized rivers and ancient oceans of Mars are not just geological curiosities, they are signposts. They point to a time when another world in our solar system might have harbored life. Understanding this history is crucial. Knowing where the water was helps us know where to look for signs of past life and where to find resources for future human explorers. The story of Mars is a cautionary tale of how a habitable world can be lost, but it is also a story of immense hope. The rivers may have turned to dust, but their memory is written in the rock, waiting for us to read it. The search for answers continues, one rock sample at a time.